Hello guys, nice to see you. So, who will remind what we were talking about last time? Something about linear momentum. So we introduced the concept of linear momentum vector and have shown that the change of linear momentum is defined by the impulse of force. Its impulse of force is the product force which is exerted on the body and time interval during which this force is exerted on the body. So with that, we follow to our next step, and we have shown that there is very nice feature of linear momentum vector in some specific system, which we call closed system, when external forces are not exerted on this system, the linear momentum vector remains constant. Means we have principle for linear momentum vector conservation, and that is quite useful feature of this parameter, which can be applied. However, we need to keep in mind that this is some idealistic model. We usually don't deal in everyday life with closed systems, and that's why we need to consider some specific conditions when this concept and principle of conservation of linear momentum can be applied. So what was the first one? Which condition should be valid in order to be able to apply conservation of linear momentum? That is the definition of closed system, but we don't have ideal closed systems. So there we consider three options when this system can be considered as closed. External forces are compensated, means net is zero. So that is when we have some block, it has some weight, there is reaction on the surface, then there is no friction between the block and the surface, and in this case, this is the case when we can assume that this system is closed. So second option. In external force is much smaller than internal. So if we develop, because of some reasons, for instance, explosion, very strong internal forces, then we can neglect with the weight of this object which was exploded. So that's the case when we, in first approximation, can consider system close to approaching this closed system condition. And the third one, when we have external force which is not compensated, however, we can build our system of reference in that way that one of the axes will be perpendicular to the external force. And in that case, for this particular direction, where the projection of external force will be zero, because it's perpendicular, we can still apply the concept of conservation of linear momentum vector. Means projections of the linear momentum on this particular axis. All other axes where projection of the external force is not equal to zero, we cannot consider as a closed system in these directions, and we cannot apply conservation of linear momentum. So that's another option how we can create conditions when it is still possible to apply this conservation of linear momentum and have benefits of this concept. So today we will consider several examples of collisions. And since collisions is the particular example where application of conservation of linear momentum is most common. And afterwards, we will learn what is center of mass of a system of many bodies or some continuous body and we'll learn how to calculate it, because later it will be quite a useful concept to be used in the future. So first, let us start with collisions. So which type of collisions do you know? Okay, that's good. So elastic collision means that during the interaction between two objects, there is no loss of kinetic energy for deformation of the objects to be in touch. And in elastic, obviously, that is the case when kinetic energy is lost for like transform into internal energy, because we have deformation of the objects. There is also perfectly inelastic collision when two objects kind of merge and form just one object which moves to already as a single piece. So let us consider first one-dimensional case when we have a collision of two objects, and perfect inelastic collision, so they kind of stick and then move together. We have some axis x. We have two objects. So with mass m1 and mass m2. So there is v1, here is v2. So we don't show here vectors for velocity because it's one-dimensional case. So the orientation of the velocity will be defined by its side, either positive or negative. So this is axis x. So now we want to model such a scenario when these guys, let's have this axis x again here, these guys collide, they stick together, m1, m2, and they move with some velocity v along axis x. So how do we approach it? We need to deal with linear momentum vector of the system before collision and after collision. So we can write that m1 times v1, that is positive orientation of linear momentum vector, because velocity from axis x. However, the client here will be negative one because we have opposite direction. So it will be now minus m2 times v2. So that is what we have before collision. And then after collision, since it's perfectly inelastic collision and two objects kind of stick together, we have total mass m1 plus m2 and times v. So from here we can easily determine mu, this velocity with which the system will move after collision. V will be equal to m1 times v1 minus m2 times v2, and divided by sum of these masses, m1 plus m2. Keep in mind here that this is our arbitrary suggestion that velocity will be along axis x. However, it may not be true because we don't know which of these possesses higher linear momentum vector. So that will be defined here. If second body possesses larger linear momentum vector, so then here we will get minus. So this will be velocity oriented in opposite direction to axis, positive direction of axis x. So keep in mind this sign, that's important. It will tell you in which direction the objects will move after collision. So this is the example of a collision along axis x, like one-dimensional case. So let us move to example when we deal with two-dimensional case. So let us consider some object with mass m1, which moves with velocity v1, and it collides with some stationary object m with a mass m2, which does like stationary, doesn't move. So here we can draw a system of coordinates with axis x and y, and let's consider that the position where these two objects collide with each other is the origin of the system of coordinate. Then they start to move at some angles with respect to axis x. So this will be m1. We need to put it here. m1. This will be m2. And here we have new velocity vectors. Will be v1 prime vector, and here v2 prime vector. We have two angles here. Let's say it's angle theta and alpha. So now we need to consider conservation of linear momentum in two-dimensional case, and we split this in direction of axis x and y. So in general, how we approach this, we can write that along axis x, we have m1 times v1x plus m2 times v2x. That should be equal to m1 times v1x prime plus m2 v2x prime. So means we have now projections of linear momentum vectors on axis x for initial case before collision and after collision. So similar, we obviously write for the other direction, so axis y. So will be m1 v1 y plus m2 v2 y, and that is equal to m1 times v1 y prime plus m2 v2 y prime. So that is the general case, and let us see what we have in this particular example. So for axis x, what is our initial linear momentum vector along axis x? m1 times v1. Yeah, because we see that it's oriented along axis x, so it doesn't have other components on y because it's parallel to axis x. So all initial linear momentum vector is oriented along axis x, so we can write it here m1 times v1. Then it should be equal to the sum of linear momentum vectors, projections of linear momentum vectors of body m1 and m2 after collision. So what do we have here? We have m1 times v1 prime times cosinus theta plus m2 v2 prime times cosinus alpha. So that is direction x. So now let us write it for direction y. Initially, we don't have any linear momentum vector along axis y, so we have here 0. That is equal, for first body, we can write m1 times v1 prime times sinus theta. And what the second component will be? minus because we see that here this second object is moving downwards with respect to axis y, so this projection of linear momentum vector on axis y will be negative. So we keep this in mind and put here minus. So minus m2 v2 prime sinus alpha. And on top of this, if we consider that this is an inelastic collision, so ideal elastic collision, we can also write the equation which stands for conservation of kinetic energy. So kinetic energy before collision should be equal to kinetic energy after collision, since we assume that these deformations of the objects during collision are negligible. So in this case, we can write that m1v1 square over 2 is equal to m1 v1 prime square over 2 plus m2 times v2 prime square over 2. So this is a system of three linear equations. Means if we have three unknown parameters here, we can solve this system of equation and get them out from there. So this is example of elastic collision in two-dimensional space. Let us consider one more in two-dimensional space, ideal inelastic collision. So for this purpose, we will consider some T-shaped cross, two roads. And two cars. So car 1 with mass m1 and velocity vector v1. And here is car number 2, m2 and v2 vector of velocity. So the drivers didn't learn well the priorities, who should go first, and they collide here at the center of this cross, and we have ideal like perfect inelastic collision, so they kind of stick to each other and move together. So in this case, we have some velocity vector v. We want to know what will be the magnitude of this velocity vector and what will be the orientation, means some angle alpha with respect to horizon, so which is defined by axis x. Obviously here we also have axis y. So what do we do here? Let's see for axis x what we have. Initial linear momentum along axis x, what is that? m1 times v1, because as you see, velocity is oriented along axis x. Along axis x, contribution of second car is equal to 0 because it's perpendicular. So then we can write that after collision we have m1 plus m2, they are moving together, and need to get here the projection of velocity vector v on axis x. So it will be v times cosinus alpha. For axis y, we can write that initial linear momentum vector will be m2 times v2. That is equal to m1 plus m2 v times sinus alpha. So we can express now velocity vector magnitude from any of these two equations. We can write v is equal to m1 v1 divided by m1 plus m2 times cosinus alpha. But we still don't know this angle alpha, so we cannot determine velocity magnitude. So in order to get it, we can divide second equation by first one. So we get the following. It will be m2 times v2 divided by m1 times v1. And that is equal to, we cancel out these masses, and the velocity. So it will be sinus alpha over cosinus alpha. That is tangent alpha. So since initial conditions are given, linear momentum vector of first car and second car, then we can get the angle alpha and substitute it in previous equation to get the velocity. So these are some examples of collisions which we consider, and now let us move forward to the introduction of center of mass. Why it's useful, we will consider this a little bit more in the light of second law of motion and conservation of linear momentum next lecture. So now we just need to define what it is and how we can calculate this center of mass. So let us start with simple example, and we'll come to some general equation which allows us to determine position vector of center of mass for different cases. So we have some axis x. One body here, a bigger body here. Here will be m1, here will be m2. So this is the origin of axis x, 0. So we can represent position of first body as x1, position of second body with coordinate x2, and obviously there, for this system of two bodies, there will be some center of mass. Assuming that the material of these bodies is the same, means density of the material is the same, so obviously center of mass will be located somewhere closer to the heavier object. For instance, if we consider planet Earth and Moon, the center of mass is located actually inside the Earth. So it's even not somewhere outside the Earth, because the mass of our planet is much higher than mass of the Moon. So somewhere here we can assume that this will be the coordinate position of center of mass along axis x for this given system. So the way how we calculate it, x center of mass is equal to m1 times x1, so mass of the first object times position of the first object, plus mass of the second object times position of the second object, divided by the total mass of this system, which is m1 plus m2. So that is this particular case, how we determine it, but it could be that we have many bodies in the system, not only two, so we need to generalize. X center of mass will be equal to sum for all objects, their masses mi times position xi, divided by the sum of masses of all objects, means mass of the system which we consider. So that could be represented as 1 over capital M. Capital M in our discussion will be total mass of the system, times sum of, for all objects, mi times xi. So that is the position of center of mass for a system of many bodies, which kind of distinct bodies. So they are defined, have defined mass and defined position. Obviously, if we deal with this example for calculation of center of mass with a system in three-dimensional space, we need to calculate position of center mass, its coordinate along all axes. So that's why we can translate this equation further for axis y and z. So y center of mass is defined as 1 over m, capital M, sum for all objects mi times yi, position of these objects along axis y. The same we write for z direction. The center of mass is equal 1 over capital M, sum for all objects mi times zi. So now we can represent position of the center of mass with as a position vector. How do we do this? RCM position vector. We obviously want to introduce now again these unit vectors. So we have position along axis x will be x center of mass times I unit vector plus y center of mass times j unit vector and plus z center of mass times k unit vector. So this is the general case of finding the position of the center of mass for a system of many bodies. However, that's not only the case. It could be that we have distributed body. So like so-called continuous body. So in this case, we don't have some individual bodies which form the system, but it's just a single body with dimensions, size, which is big enough that we cannot consider it as a point with some coordinate x, for instance. So in this case, what we need to do? We need to kind of divide this continuous body in small segments and deal with them as they are individual objects. So let's say we have some arbitrary shape distributed body. Let's say three-dimensional body. Then we pick up some small element of this body with mass dm. And in this way, we can represent it in the whole body as a combination of these building blocks, many these building blocks. So in this case, we consider that x center of mass for limit that delta m approaches to 0, that we pick up very small elements of this body and we have equation for position of the center of mass, 1 over capital M. Total mass of the system means mass of this continuous body times sum for all small segments of this body for xi times delta mi. So when delta m approaches to 0, so we deal with very small blocks, units of this continuous body, we end up with an integration. So it will be 1 over capital M integral for x times dm. So obviously we can write the same for position y center of mass and z center of mass. And in general, if we want to represent for two and or three-dimensional cases, we deal with the position vector of the center of mass. and that is equal to total capital mass, capital M, total mass of the system, um, times integral of position vector dm. So that's the general approach how we determine center of mass for also in the case of continuous body. Now let us try to consider some examples how we apply these equations to calculate center of mass for some simple continuous body. So first we will make it quite simple. That will be some rod. So this is axis X. This is length of this rod will be L. So here is the origin of axis X, 0. We need to describe some properties of this rod in terms of mass distribution. So it will possess some linear mass density, like linear density, and this is considered at this first step as constant. So we have constant distribution of mass along this rod, so it's not a function of position x, and this rod has length L. Any suggestions where will be center of mass for this system? In the middle, you're right. Since we have kind of a symmetric case, if we divide this rod in two pieces, like two halves, they will be identical, so center of mass will be in the middle. So that's our intuitive suggestion, which makes sense, but let us do it quantitatively. So we assume that center of mass should be here. So how do we approach this? We need to divide this rod in small elements with length dx and coordinate like position x. Now let us recall what is the equation for position of the center of mass along axis x. It will be 1 over capital M integral x dm. Let us write it here. So x center of mass will be equal 1 over capital M integral of x dm. So how we represent this dm in terms of x? Obviously, this small element which we pick, it will possess some mass. It will be dm. How we represent this dm? Assuming that we have linear density lambda.
Lambda multiplied by x.
Multiplied by d.
Yes.
dx. Yeah, so this small length. So dm we can represent as the length of the segment times linear density. So dm will be equal to lambda times dx. Following this, we can also write that the total mass of the rod, capital M, will be equal to lambda times L, which is the length of the rod. Now we substitute instead of dm lambda times dx and continue. So it will be 1 over capital M integral. Now we can define it. It will go from 0 to L. We go through whole length of the rod. And here will be x times lambda dx. So lambda is a constant, so it can be taken out from the integral. Lambda over capital M integral from 0 to L x dx. That is equal to lambda over capital M x square over 2 from 0 to L. And eventually here we get lambda times L square divided by 2 capital M. So now we want to substitute, instead of the total mass of the rod, its expression in terms of lambda and L. So if we do this, can write it here, will be lambda times L square over 2 times lambda L. We cancel out lambda, cancel out L in the denominator and square in the numerator, and we end up with L over 2. So it looks like our intuitive thinking makes sense. In this case, we indeed got a position of the center of mass right in the middle of the rod. So now let us make it a little bit more challenging. And challenging, it's easy to make. We just make it not symmetric. So we have the same rod, like everything is the same as in this example. However, we already do not consider that lambda is constant, means linear density is constant. Let us assume here that lambda is some linear function. It's some coefficient alpha times x. What does it mean? It means that as we go along axis x, the linear density of this rod linearly increases according to this equation lambda times x. Lambda is equal alpha times x. So now what is suggestion where the center of mass should be?
M equals to lambda x
Now, yes, you're right. So if we L rate of this small element, instead of lambda, we substitute alpha times x. But the question before we go for calculations, where, from your point of view, this center of mass will be located?
right.
So it will be shifted to the right side because as we go from left to the right, this rod becomes heavier at the right side. However, at this point, you cannot tell me exactly where it will be. So we can only suggest where it moves, like shifted towards the right of the part of the rod. However, we need to run certain calculations because this case is a bit more difficult in comparison to the first symmetrical one. So again, what will be our x center of mass will be equal to 1 over capital M integral from 0 to L. And here we have x. Instead of lambda, we substitute alpha times x. And here is dx. So alpha is a constant, so we can take it out from the integral. We have alpha over capital M. Here we have integral from 0 to L, and this is x squared times dx. So what this integral will give us? Will be x cubed divided by 3. This is not good. X cubed divided by 3 from 0 to L. So we can write here that the position of the center of mass will be equal to alpha times L cubed divided by 3 capital M. Well, at this point, we still don't know where the exactly it's located because we need to define this capital M. What will be capital M?
It will be lambda x L.
You still have x. Yeah, you don't need to have x in your final equation. So how we deal here? Before it was simple because we just multiply uniform lambda by L. But here we need to determine
Integral lambda x.
so so we need to total mass will be equal to integral, you're right, from 0 to L. And here we can write dm. And dm, how we represent it? It was lambda times dx, and lambda is alpha times x. So here we can write integral from 0 to L alpha x times dx. Alpha is a constant, so we take it out from the integral from 0 to L x dx. Here we get alpha times x squared over 2 from 0 to L. And that is equal to alpha times L squared over 2. So that is the total mass of the rod. And as you see, we don't have x, it's just defined by the total length of the rod. Now we can substitute it here for capital M in our previous equation for position of the center of mass. So we have alpha times L cubed over 3 times alpha L second power, and 2 we can put here in numerator. So we cancel out this alpha, we cancel out L second power in the denominator and this cube in numerator. So we end up with 2/3 L. So as you may see here, if we come back, so our new center of mass will be indeed shifted towards the right side, and this will be already 2/3 of the length of this rod. So this is the example how we can apply our equations to determine position of the center of mass. Obviously, quite simple example, but it provides you a feeling how this should be done. So during this lecture, we considered some applications of previously introduced principle of conservation of linear momentum based on consideration of different collisions in one and two-dimensional cases. So we deal with elastic and perfectly inelastic collisions, where we apply this concept of linear momentum vector conservation. And we introduced a concept of center of mass. So it's quite useful because we can represent translational motion of a system of bodies or some continuous body with the translational motion of a single point, which is center of mass, assuming that whole mass of the system is concentrated in this single point. So we will talk about this in more details next lecture. But what is important, now we know how to determine position of center of mass for either single or multi-dimensional cases, and considered some examples. Thank you very much for your attention. See you next time on Friday.